look at the phone in your hand or the car you drive and just wonder, how in the world do we make these incredibly complex things so affordably? I mean, we're talking about thousands of individual parts coming together, not just once, but millions of times over with absolute ruthless efficiency. Well, today we're going to unlock that very puzzle, the puzzle of mass production. Seriously, just think about a car for a second. It has something like 30,000 parts. 30,000. From tiny little screws to the massive engine block. If you or I tried to build one in a garage, it'd take us a lifetime and cost a fortune. And yet factories are cranking them out every single minute. The secret sauce isn't just about making a lot of things, it's about a revolutionary method for making them. So here's our game plan to figure this all out. We're going to start with the revolution that kicked this whole thing off. Then we'll look at the money. When does it actually make sense to build a massive assembly line? After that, we dive into the really juicy stuff, the line balancing puzzle. We'll see how engineers solve it, and finally, we'll check out the flaws in the classic system and the super clever ways we're fixing them today. All right, so let's get started. Before we get into the nuts and bolts of the line itself, we kind of need to zoom out and see where it fits into the whole world of, making stuff. Generally, you can sort production into three big buckets. On one end, you have a project. Think building a bridge or a skyscraper. It's a massive, one-time thing. Then you've got the job shop. This is like your local custom machine shop. They can make 50 unique gears one day and a couple of metal brackets the next. It's all about being flexible for small, varied orders. And then you have the flow shop. This is our turf. This is where the mass production magic happens. It's a repetitive, step-by-step process designed to churn out a huge volume of the exact same thing, like a car. And this is the key. When Henry Ford rolled this out back in 1913, the term mass production wasn't just about making a ton of stuff. It was all about the method. It's this idea of breaking a huge, complex job down into the smallest possible tasks, and then arranging those little tasks in a perfect flowing sequence, an assembly line. But here's the catch. An assembly line is a huge, expensive beast. You don't just build one for fun. So how does a company decide when to pull the trigger? Well, it all boils down to a pretty straightforward economic trade-off. Okay, this chart right here lays it all out perfectly. Let's walk through it. Up the side, you've got your total cost, and across the bottom, you've got how many units you need. That first line, the lowest one to start, that's just buying the part from someone else. The middle line, with that $10,000 upfront cost, is making it yourself at individual workstations. And that top line, with a big old $20,000 fixed cost, that's our assembly line. But look closely. See how its line is the flattest? That's because the cost to make each individual part is super low. So those points where the lines cross, those are your decision points. It's simple. If you need less than 2,000 parts a year, don't bother. Just buy them. If you're somewhere between 2,000 and 4,000, yeah, it's cheaper to make them yourself, but without the full line. But the moment you need more than 4,000 units, bingo. The assembly line, despite its high startup cost, becomes the cheapest option by a long shot. It's all about volume. Okay, so you've run the numbers and decided to build the line. Awesome. Now comes the really hard part. Getting that line to run like a well-oiled machine isn't just about lining up some equipment. No, it is an incredibly tricky puzzle that engineers spend their careers trying to solve. And this right here? This is the rulebook for our puzzle. It's called a precedence diagram. Every circle is a tiny task, and the number inside tells you how long it takes. And the arrows, they're the rules. They show you what has to happen before something else can. So for example, you can see you absolutely cannot start tasks 2 and 4 until task 1 is totally done. And way over on the right, task 12 is stuck waiting until tasks 8, 9, and 11 are all finished. It's this tangled web of rules that makes balancing the lines such a headache. And now let's add a ticking clock to our puzzle. This is called cycle time, and it's basically the heartbeat of the entire assembly line. If your goal is to have a finished product roll off the line every 60 seconds, then your cycle time is 60 seconds. That means the total amount of work done at any single workstation cannot, under any circumstances, take longer than 60 seconds. It is the ultimate speed limit. Which brings us to the villain of our story, balance delay. Just imagine one workstation takes 58 seconds to do its job, but the next one only takes 40 seconds. What happens? Well, that second worker is just sitting around twiddling their thumbs for 18 seconds every single cycle, waiting for the next part. Now add up all that wasted idle time across the entire line. That's balance delay. It is pure unadulterated waste, and killing it is the name of the game.
So we've got our rulebook from the precedence diagram, and we've got our speed limit from the cycle time. How in the world do we group all those little tasks together to defeat that villain, that balance delay? Well, let's see how the puzzle gets solved.
The goal itself is pretty simple to say, but it's way harder to actually do. You have to bundle those individual tasks into workstations. And the trick is to make the total time for each bundle as close to the cycle time as you can get without ever going over. It's all about creating this perfectly smooth, even rhythm for the whole production line. So here's our puzzle board again. All the pieces are laid out. We've got our 12 different jobs, each with its own time. Our cycle time, our speed limit, is 10 minutes. So how do we group all this chaos into the smallest number of super efficient workstations? And voila, here's the solution. Those 12 scattered tasks are now perfectly bundled into 6 neat workstations. Just look at workstation 5 over there. Tasks 8 and 11, they add up to a perfect 10 minutes. Right on the money, exactly our cycle time. Chef's kiss. Other stations, like the first one, are just under at 8 minutes. By grouping them this way, we've created that smooth, efficient flow we were talking about. And we've minimized all that wasteful idle time. Puzzle solved. Now, don't get me wrong, the classic assembly line was a monumental achievement, a game changer. But it wasn't perfect. It actually had some pretty serious flaws. So let's take a look at those weaknesses and then at the modern fixes designed to overcome them. You see, the classic line was all about trade-offs. On one hand, you got this incredible efficiency, smooth flow, crazy fast production, super simple training for workers. But the downsides, they were huge. If one little machine broke down, the entire line screeched to a halt. The whole system was incredibly rigid. Want to change the product design? Good luck. That could mean a massive, expensive overhaul. And honestly, the work could be incredibly monotonous. So the system is powerful, but it's brittle. It's efficient, but it's totally inflexible. How do modern factories get the best of both worlds? Well, they use some really clever strategies. Okay, first up, modular production. Instead of one person tightening the exact same bolts all day long, you have a team of workers assemble an entire dashboard, the wiring, the gauges, the whole shebang. This complete module can then be dropped into a sedan, an SUV, maybe even a truck. It makes the work way more interesting and gives the company a ton more flexibility. It's a win-win. Next, we have group technology. This is all about organizing how you make the components in the first place. Instead of having machines scattered all over the factory floor, you create these little dedicated work cells. So, for example, all the parts that are basically round shafts get made in one cell that has all the right equipment for that family of parts. It kind of blends the efficiency of a flow shop with the flexibility of a job shop. And of course, you knew it was coming, robots. But the key thing to understand here is that modern industrial robots are a form of flexible automation. A robot that's welding a car door today can be reprogrammed to assemble a totally different part tomorrow. They give you the speed and the precision of a machine, but with the adaptability that those old, rigid assembly lines could only dream of. Which leads us to one last thought to chew on. We've come all the way from Henry Ford's rigid, unbending line to these flexible, robotic cells. As AI gets smarter and automation gets even more advanced, will we one day create the perfectly balanced, completely optimized factory that can adapt to anything in an instant? Or is manufacturing just so fundamentally complex that there will always be a need for that human touch, for human ingenuity to solve the next unforeseen puzzle?